look at this problem. They say that a skier is just sliding down, at 3 meters. That means this is just, it's just a sliding, along a 3 meters per on a flat surface, because it's basically what is happening first, at 3 meters per second on a horizontal flat surface, a frictionless surface of a snow, right? And then suddenly start down a 10-degree incline, so that the speed at the bottom is 25 meters per second. So look at this, right? Let us first make a diagram to try, to understand what is going on. So we have here a sky, right? That is just going in that direction at 3 meters per second. This is constant, 3 meters per second. So when it's here, right, it's at 3 meters per second. But then there is an incline here with an angle of 10 degrees. Okay? And it's going to slide down, right? And at the bottom, it means at this point, the velocity would be what? 15 meters per second. So this is the initial velocity. This would be the final, or the initial speed and the final speed, right? Now, what is going on here? I have a 10-degree inclined plane, right? So the first is to analyze, because the first question here is, what is the length of the incline? So I want to find the distance from this point to this point. So that would be L, the length of the incline, right? Now, what we have to keep in mind when we have a problem like this one. Let us make a free body diagram, right? So I have 10 degree here. Doesn't matter what is sliding down here, a person, a box, or a particle, whatever is just sliding down, so I will just represent like kind of box here, like this. You have here the gravity. The acceleration of the gravity, right? And now what happens? That the angle of this acceleration of gravity with a perpendicular to the surface of the incline would be the same that the angle of the surface of the incline respect the horizontal. So this angle here would be 10 degrees. Okay? This is my angle of 10 degrees. So what I have is the acceleration of gravity here. So we have two components of this acceleration of gravity. And we have one component parallel to the surface of the incline that I will call A parallel. And we're going to have one component that would be perpendicular to the surface of the incline, right? One that would be perpendicular. Let me see what other color can I use. This one maybe. I'll call this one acceleration perpendicular, right? Now, what is a parallel? The acceleration parallel to the surface of the incline is what is making the body to slide down the incline, right? That acceleration, parallel to the surface of the incline is what makes the body to slide down, right? But it's gonna favor You know, that the body slides down and increase its speed and its velocity, right? So now, what is the magnitude of this acceleration that is parallel? Is the opposite side to the angle of 10 degrees. So this parallel acceleration, as you can see here, you know, is opposite side to this angle of 10 degrees. So A parallel would be G sine of theta. If theta is 10 degrees, it would be 9.8 meters per second square sine of 10 degrees, right? So this acceleration parallel is 1.7 meters per second square. So this acceleration is the reason of my increase in velocity, right? The acceleration perpendicular, the perpendicular component of the acceleration is not going to play any role here into the motion slide down incline, right? So what I have to use as acceleration here is the parallel acceleration, the parallel component of the acceleration. So first, do you understand this analysis that I have done about the components of the acceleration? Do you understand?
Yes, Professor.
Okay, so it's pretty clear for you that we have two components, one parallel component, one perpendicular component to the inclined plane, right? And only the parallel component of the acceleration is involved into my body sliding down incline and gaining velocity. So if I know the initial velocity, if I know the final velocity, if I know the acceleration, and I want to find the length, what formula can I use that just involve all these variables, that just put together all these variables, right? We have one formula here to say that the square of the final velocity is equal to the square of the initial velocity, right? Plus 2 times, I'm going to say the parallel component of the acceleration times L, right? When this is just in a horizontal surface, instead of L, I will say this is delta X. It's the same. Or when I am in a vertical surface, you know, I will say that this L is just delta Y. I am not call now this neither delta X, delta Y, except if I just put a new coordinate system here like this, but I say this is Y, this is X. I can do that. If I want, I can do it, right? But anyway, it's not necessary really, right? So I would just call this L and enough. It's the length of the incline. So what is the final velocity? 15 meters per second square. The initial velocity is 3 meters per second square, plus 2 times 1.7 meters per square second times L, right? So I can now solve here for L. You can say that 15 meters per second square minus 3 meters per second square over 2 times 1.7 meters per second square is equal to L, right? So L would be approximately, 63.5 meters, but it's the same as 64 meters. So what is the length of the incline? The length of the incline is approximately 64 meters. 64 meters. So any question about how I found the length of the inclined plane? So
No questions.
look at this. Here, you know, to find acceleration, what I had to do was basically say, okay, I know, you know, that I have uh, an inclined surface. So the acceleration of gravity that points always toward the center of the earth, so it's always vertical, will be break down here into components, right? One perpendicular component, one component perpendicular to the surface of the incline, one component parallel to the surface of the incline. And then only the parallel component is part of, you know, this problem where we have, you know, these bodies sliding down and gaining some velocity. Now, the second part here is how long does it take him to reach the bottom? You know, so now we want to know how long it takes for this guy, you know, to reach the bottom of the inclined plane. So now it would be easier because now we know the final velocity, we know the initial velocity, we know also the acceleration, that is the parallel component of the acceleration, and we want to find the time. So I can say here that BF is equal to V initial plus acceleration time. So in this case, BF is equal to V initial plus my parallel component of acceleration times the time, right? So if I replace BF by its value, this is 15 meters per second equals V initial is 3 meters per second plus the parallel component of the acceleration is 1.7 meters per second square times the time. I solve for time. And we get 15 meters per second minus 3 meters per second divided by 1.7 meters per second square equals time. So the time would be, in this case, 7.06 seconds. You know what is equal to 7.1 second. 7.1 second. So how long does it take him to reach the bottom? 7.1 seconds is what takes, right, to the skier to reach the bottom of the inclined plane. Okay? So this is the second part of the problem. This is A, and this is B. Any question?